is going to be on how do seismic waves travel. In the last part of these notes, which is notes 3.1, part 1, we talked about how the layers were formed, and we talked about that the Earth has layers. We have two models of the Earth. We have a physical layers model, and we have a compositional layers model. So with that being said, one of the things that people ask, well, how do we know what these layers look like, or how do we know that the outer core is liquid? So one of the pieces of evidence that scientists use are seismic waves. And there are two types of seismic waves that travel through the Earth and provide information about Earth's interior, are P waves and S waves. The speed and direction that P and S waves travel depend on the properties and the materials they travel through. Both types of waves generally travel faster in rigid, dense rock and slower in less rigid and less dense rock. Translation, that just means that if a wave travels through the earth, if the material is thick, like a solid, it's going to travel pretty darn fast. If it's not as thick or less dense, then it's going to travel slower, like through a liquid. So the first type of wave that travels through the Earth are P waves. We call them P waves, short for primary waves. They're the first wave to arrive at the surface. They're also known in some cases called compressional waves or longitudinal waves. The reason why is because these P waves press or squeeze or compress rock, and then they expand the rock, hence the term compressional waves. And the reason longitudinal wise is that when you look at a map, they go, the degrees go left to right. Well, longitude is left to right, so this is a longitudinal direction. It's going left to right or back and forth. Okay, if you were to actually look at this in a more visual way, I'm going to show you this website. Here you can see a set of longitudinal waves. Okay, it looks like the waves are traveling from the left to the right, but if you look carefully, follow one of these dots, specifically the red dots. You're going to notice that the particle actually just goes back and forth. It doesn't actually travel all the way down. It's just an optical illusion. The bottom part of the screen gives you kind of a better idea of how the particles go back and forth, and the wave's energy forces it down this way. So that is a longitudinal, or what we call a primary wave. Imagine this was rock. It would just go back and forth, back and forth. Then if you move on, you have the secondary waves, also known as S waves, and they arrive second after the P wave. These rocks move up and down or side to side. Sometimes they are called transverse waves. S waves can only be detected moving through solids. So an easy way to remember this is S waves or solely solids. That's an easy little tongue twister for you to remember, that S waves can only travel through solids. So S waves, solely solids. There is a video clip that you're going to watch next. Now, I'm going to warn you right now, the guy's hair is like really old style. He's a professor. So if you can get over his hairstyle and watch what he does and listens to how he explains how waves travel through P and S waves and why they don't travel through, S waves don't travel through liquids, you'll actually truly understand the difference between the two. Just get over his hair. Okay? All right, go ahead and watch this video.
And I'm here to give a demonstration to help better understand some of the basic concepts of seismic waves. Seismic waves are vibrations generated in the Earth's interior that carry energy away from the focus of an earthquake, from the initial rupture of an earthquake on a fault line, to carry that energy away towards the surface where we experience that as a ground shaking that we call an earthquake. So this demonstration will look in particular at a particular category of seismic waves called body waves. Body waves are those seismic waves or those vibrations that travel through the Earth's interior as opposed to along the surface of the Earth, which we call surface waves. And there are two basic types of body waves. These are called P waves and S waves. And our objective in this demonstration is to show some of the distinctive characteristics of P and S waves. All right, what I'd like you to do, I have a group of courageous student volunteers who are going to help me do this demonstration. So I'd like you to do is line up here as a line. And let's see here. You come here to this end. That's really cool. What I want you to do is I want you to all turn and face that direction. Right? Now, what I want you to do is put your hands out in front of you, grab the shoulders of the person behind you, and lock your elbows. Keep them straight, not just lock them straight. Okay? Firmly gripping the person in front of you. Okay? Now, what these students represent is individual atoms in a solid. Okay? So their connection, their gripping each other, represents the chemical bonds that hold atoms rigidly in position relative to each other. Okay? So they're holding the person in front of them, gripping them tightly. So this is an illustration of the chemical bonds in a solid that are holding atoms in a rigid position. Okay? Yeah, so everyone's in position, everyone has their elbows nice and locked, right? Okay? So for this first demonstration I'm going to give is for a P wave. P waves are compressional waves. That is the motion of the molecules in the solid as a seismic wave passes through is in the same direction as the wave propagates through the material. Okay? So the motion, the vibrational motion of the atoms is in the same direction as the wave travels. Okay? So what you've seen is made an impact here, so that would be like the initial rupture of the earthquake fault line. And that energy, we're talking about the transfer of energy, that energy is being transferred from atom to atom by way of the chemical bonds that hold them rigidly in position. Okay? Now, which would be something else, which is now turn and face this direction. All right. And now instead of putting your arms on each other's shoulders, put your elbows out like on a little teapot and interlock. Okay? So again, you want to be firmly locked together. And we'll step forward a little bit here. That way. Okay, cool. Perfect. Okay, we're still doing a solid in which the atoms are locked together. Now the locking of arms is illustrative of the chemical bonds holding them together. But instead of doing a P wave, we're now going to do an S wave. Okay? Now in an S wave, the motion, the vibrational motion of the atoms is actually perpendicular to their direction of propagation through the material. So now the atoms, the material, and the vibration is actually moving at right angles to the direction that the waves are traveling down the line. Okay? Everyone all nicely locked together? Okay? Okay? Notice I've been able to send the energy down the line. This is a solid. Everyone's locked together. Atoms are locked together in a solid. And again, I can transfer that energy. In this case, it's a shearing energy, a shearing movement. But I can transfer it through the material if it's a solid. Okay. Now we're going to do something different, showing a different type of material. I want you to, again, stand back to back. Not back to back, front to back, sorry. Facing that direction. And put your arms out in front, like you did before. Except in this case, don't grab the person in front of you, back up a little bit, so that there's maybe, an inch or so between you and the person in front. Okay? Everything is still, you still want to lock your arms rigid, okay? But you're not grasping onto the person in front. Okay? Okay, now this is, instead of being a solid, what we're trying to illustrate here is a liquid. Okay? So we have the atoms that are still fairly close to each other, but they're free to move relative to each other. They're not held together rigidly by chemical bonds. So they're actually not connected to each other by chemical bonds. So first illustration I'm going to do here again is for P wave, P seismic wave, which means a compressive wave, in which the motion is in the same direction as the wave. So we'll see what happens in this case. Okay. Notice that we have the same response. Okay? We have a solid, we have a liquid, and they both respond in the same way. In both cases, I'm able to send that compressive wave to the material, the drop drops. Now, it's important to realize that a compressive wave, not only can it travel through a solid, it can also travel through a liquid, and it can also travel through a gas. We call those sound waves. So a compressive wave can actually travel through any type of material, any state of matter, solid, liquid, or gas. It doesn't matter that a pressure wave or compressional wave, or P wave, will be able to travel through any kind of material. Now let's see if that's the same case with an S wave, right? Now, again, line up like you did before, facing out with your arms out, but again, don't lock. Okay? So, same kind of situation, you're not locked. Okay? So, we're in the same position, we're still close together, right? So the atoms are still close together, but they're, again, not bound to each other, not chemically bound to each other. So now we want to see if we can send a shearing wave. That is a wave in which the motion is perpendicular to the direction that propagates the material. Right? Everyone ready? Notice that I cannot send an S wave through the material. And that's because there's no chemical bonds. The only way that the energy can get transferred through an S wave is through those chemical bonds. If they're not present, you cannot send the energy through the material. So imagine if you're in a swimming pool or some body of water, right? You can send a compressive wave through that body of water. But if you try to send a shearing wave, like you want to send a wave that way, you can't do it by trying to push the water this way. It's not going to go that way. You can't propagate a wave, an S wave, through a liquid. So one of the important distinctions between a P wave and an S wave, P waves are compressional, and S waves are shearing waves. P waves can travel through any state of matter, but S waves can only travel through a solid in which the atoms are bound to each other.
Demonstration of P and S waves. What is that? What do P and S waves tell us about Earth's interior? What scientists do, they calculate the times the P and S waves take to travel from an earthquake to different seismographs all over the world. Seismographs are those machines that record earthquake movement. You've seen them before if you've ever watched any type of earthquake video. I can even show you one. Seismograph. Okay. These are your typical seismographs. Okay, here this is a great example of one wherein you'll see this is the P wave, and then you'll have the S wave, and then you'll have the surface waves. P waves come first, S waves come second, then surface waves come last. Surface waves, as you can tell, when you get the surface waves, those are the waves that stay above or stay on the Earth's surface, and they're the most destructive. Okay. Going back to our presentation, as seismic waves travel through Earth, they reach different areas when they abruptly change speed and direction. They bend or reflect off of certain material. These changes in speed of seismic waves occur when these waves pass between layers. There are major changes in properties such as composition. For an example, at the boundary between the crust and the mantle, the seismic wave abruptly increases in speed. That's because the mantle is less rigid than the crust. Okay, P waves suddenly slow down as they bend through the outer core and then speed up and bend again as they pass through the inner core. This is evidence that the outer core is liquid and the inner core is solid. The area of missing P waves is called the P wave shadow zone. So let me show you what that looks like. So here, when you start an earthquake, what happens is the seismic waves ripple through the solid part of the Earth. That would be the crust and the mantle. Then when they hit the liquid layer, they bend, or what we call refract. So notice how these waves don't travel in a straight line. They actually travel here, then curve, and here curve, and then curve again. So the area that's here are areas wherein the wave doesn't actually travel to, so we call those shadow zone. Now notice how small these shadow zones are. So if the earthquake started here at the top and I had a seismogram here, or graph here, then it would detect that earthquake, and we could eventually pinpoint the location of where the earthquake started. Unlike S-waves do not reach seismographs on the opposite side of the Earth of an earthquake. This makes a circular area of missing S-waves called the S-wave shadow zone. Scientists deduce that the zone exists because S-waves reach the liquid outer core and they cannot travel through it. So in this case, on the left-hand side, you've got P waves going through. On the right-hand side here, you've got S waves going through. And because the outer core is made of liquid, it's not going to go all the way through like it does the P wave. So the S wave hits the outer core, stops, and then turns to other directions. And then you'll notice the S wave shadow zone is much bigger than the P wave shadow zone because of this hole not being able to get through the outer core. So if you combine the two together, you'll actually get your evidence of how they know that this outer area is made of liquid, since the S wave cannot travel through, and that there must be a solid center because the P wave tends to change directions again, and then it goes through the other side, each time passing through a layer, changing directions. So with that being said, that is it for seismic waves. You'll have a quiz on it coming up soon, so if I were you, I would review European S waves and maybe watch over this part of the video again. All right, with that being said, see you later.